All right, let's get into it. We use the word electricity all the time, but have you ever stopped to think about what it actually is? What's really happening when a current is flowing? Well, today we're going to break down one of the most important forces that powers our entire world, and we're going to look at it in a way that might just surprise you.
So, to get started, just close your eyes for a second. Well, not literally. You need to see the screen. But picture this. You're just floating down a river. Maybe it's a lazy, calm stream, or maybe it's a powerful, rushing rapid. That image, right there, the simple movement of water, that's going to be our key to unlocking the secrets of electricity.
So you're probably asking, okay, a river. What on earth does that have to do with the phone or the computer I'm watching this on right now? And the answer is pretty much everything. It turns out that flow of water is an almost perfect analogy for the flow of tiny particles, electrons, through a wire. And trust me, by the end of this, you'll see exactly how. Okay, first things first. A river doesn't just flow on flat ground, right? It needs a slope. It needs to go from a high place to a low place. It needs that downward push from gravity to get it moving. Well, electricity is exactly the same. It needs a push too. And that push has a name: voltage. Now, this slide calls it electric potential difference, which I know sounds a little technical, but all it really means is that there's a difference in energy between 2 points. Just like the river flows from high ground to low ground, electrons flow from a point of high energy to a point of low energy. Without that difference, without that drop, you get nothing. No flow. It's that simple. For a long time, scientists could only make these little zaps of static electricity. They were totally unpredictable and gone in a flash. The real game changer was a guy named Alessandro Volta. He figured out how to use chemical reactions to create a constant voltage, a steady, reliable push. This was huge. It was like he built the world's first dam and spillway, creating a continuous controlled river of electricity for the very first time. In that brilliant invention, it's pretty much what's inside every battery we use today. Seriously, when you look at a battery, just think of it as a stack of Volta's little cells. Each cell adds its own push, so when you combine them, you get a stronger total voltage. That's all a battery is. All right, so we've got the push, that's voltage, but now we got to talk about what's actually flowing. And more importantly, how do we measure that flow? So here's the key idea. Current isn't just about electrons moving. It's about the rate they're moving at. Let's go back to our river. Imagine you're standing on a bridge and you're counting how many gallons of water flow under you every single second. That's current. For electricity, we're just counting how much charge, how many of those little electrons, zip past a single point in the wire each second. And of course, we've got a special unit for this, the amp, which everybody just calls an amp. So if you hear that something uses 1 amp of current, all that means is that 1 coulomb of charge, which is just a fancy name for a huge number of electrons, is flowing past a point every single second. Okay, get ready, because here's a classic bit of science confusion we need to clear up. Way back in the day, Benjamin Franklin had to guess which way the charge was flowing. He took a 50-50 shot and said it flowed from the positive side to the negative. Well, turns out, he guessed wrong. The actual electrons, which are negatively charged, flow the other way. But by the time we figured that out, the original convention had totally stuck. So today, when engineers talk about current, they're almost always talking about conventional current, from positive to negative, even though we all know the electrons are really moving from negative to positive. Kind of weird, right? Now, back to our river. It doesn't always flow perfectly smooth, does it? It runs into stuff: rocks, fallen trees, narrow channels. The same thing is true for our electric current. And this brings us to our third and final key concept: resistance. I mean, think about it. A big, wide, deep river, water just cruises right on through. But a narrow, shallow channel that's totally choked with rocks and branches, that's going to slow the water way, way down. Well, those obstacles are resistance. In a wire, the atoms of the material itself acts like those obstacles for the flowing electrons. And we measure this opposition in a unit called ohms. Something like a copper wire has super low resistance. It's that wide open river. But think about the tiny little filaments in an old light bulb. It has incredibly high resistance, and that's on purpose. It's like a deliberate traffic jam for electrons, forcing them to work so hard to squeeze through that they get super hot and start to glow. And that glow is light. So, this little table right here, this is the whole shebang. It puts it all together perfectly.
Voltage is the push, a river's elevation drop. Current is the flow, the amount of water moving, and resistance is the obstacle, all those rocks and branches getting in the way. If you can remember this analogy, you've pretty much got the fundamentals of electricity down.
And what's so amazing, so elegant, is that these three things are all linked together by a beautifully simple piece of math called Ohm's law. All it says is that the push you get, the voltage, is equal to how much flow you have, the current, multiplied by whatever obstacles are in the way, the resistance. So let's make this real. Say you take a standard 9-volt battery, that's your push, and you hook it up to a light bulb that has 15 ohms of obstacles. Ohm's law tells you exactly what the flow is going to be. You just divide the voltage by the resistance, and you find out the current is 0.6 amps. It's not magic, it's physics. We can actually calculate this stuff.
So we've got this flow, we've got this current. But so what? Why do we even care? Well, the whole point of all this is to make those flowing electrons actually do something useful for us. And that's where circuits and power come into play.
A circuit is just a closed loop for the current to flow around. The simplest kind is a series circuit. You know those old, super annoying holiday lights where if one single bulb burns out, the entire string just dies? Yep, that's a series circuit. There's only one path, so a break anywhere kills the whole thing. That's exactly why our houses are wired up with parallel circuits. They give the electricity multiple paths to take, so you can turn on your lamp without also having to fire up the blender.
So when that current flows through a device like your phone or a lamp, it does work. It turns that electrical energy into something else, like the light from your screen or the heat from a toaster. The rate at which it does that transformation, that's what we call power, and we measure it in watts. And hey, guess what? Just like Ohm's law, the math here is beautifully simple. The power something uses is just the current flowing through it multiplied by the voltage that's pushing it. A bigger push or a stronger flow means you get more power. It just makes sense.
This quote from one of our sources, CrashCourse Physics, just nails it. It says, "The whole point of batteries isn't to just push electrons around. We need to put those electrons to work." And that's exactly it. We don't build these massive, complex systems just to watch electrons go in circles. We do it to make them work for us.
And that kind of brings us to a final mind-bending thought. We've learned that resistance is the natural obstacle, the thing that always gets in the way. But what if you could have a path with zero resistance? Well, materials called superconductors can do exactly that. They're like a perfect frictionless river for electricity. So I'll just leave you with this question. If we can create a perfect path with absolutely nothing to slow the current down, what currently impossible things could we power next?